Welcome to another math video lesson. Today we're talking about natural logarithms, okay? At the end of this lesson, we will be able to evaluate exponential equations and logarithmic expressions that involve natural logs, okay? So let's hop right into it. Okay, so far we have seen common logarithms, okay? That is a log with a base of 10, right? Okay, but for our natural logarithms, that is going to be a log with a base of e, okay? Now you're not going to see it written like this, and you shouldn't write it like this either, because a more common way to write a natural log is going to be ln x, okay? So this is our natural log of x is how we would say that. Okay, natural log of x. So write it as ln of x, not like this, okay? Now you might be thinking, if you haven't seen e before, you might be thinking, well, what is e? E is going to be what is called Euler's number, okay? Euler's number is e. Okay, now Euler's number looks like 2.71828, okay, and it just keeps on going, okay? This is like pi, like the square root of 2, okay? This is an irrational number, all right? And how we kind of get Euler's number, all right, it comes from this concept of like our compound interest, right, that we saw in a previous video. Okay, so to kind of derive our Euler's number, we're going to go ahead and say, what if we invested $1? Okay, so our P is 1, and then our time is going to be for 1 year, and our N is our number of compounds, okay, in that year. Okay, so this is kind of the parameters that we're using to set this up, all right? So, and we're going to say our rate is, say, like 100%, all right? So this is going to be a 1 right here for our rate. Right? Which is possible, right? If you're doubling population, okay, you have this doubling in mass of molecules or whatever it might be. Okay, so R is going to be 1 in this case, or 100%. 100%. Okay, so what would happen if we were to compound one time, okay, throughout our year? We just compounded once throughout our year, then we just have, okay, our P is always going to be 1 right here, okay, so I'm not going to write that moving forward. And then our T is 1, okay, but then our R, again, is going to be 1, and our N then would be 1 if we're just going to compound one time per year, okay? So now I have 1 plus 1 raised to the 1, so that is just going to be $2, okay? So our principal becomes $2 from $1, all right? Not bad at all. However, what happens if we go ahead and compound our interest, let's say monthly, okay? So over the course of a year, we would have 1 over 12 now raised to the 12th, okay? And then inside here, we got 1 plus that 1 over 12, okay? If you calculate that out, we would get $2.61, okay? So a pretty good jump there. Now, what if we went ahead and we compounded every minute? Okay? So now my N is 365 times 24 times 60, okay? So every minute we're compounding this interest. Okay, so now I've got 1 plus 1 over, okay? This is going to be 525, 600, all right? And then raised to the 525, 600. And what we get if you plug that into your calculator is going to be this 2.71828 and probably more decimals, okay? And that's starting to look like our Euler's number, right? So really what this Euler's number is, because mathematicians always have to create these fancy concepts for all this stuff, right? Okay, so if I have A is equal to 1 plus 1 over infinity raised to the infinity, okay, that's what this Euler's number really is. That equals E, our Euler's number. So that's where we get this number from, and it has a lot of really cool applications, especially in calculus and for other classes. But for now, we're going to take a look at it in terms of our logarithm. Okay, another concept for this lesson, we're going to look at continuous compound interest. Okay, we've got this equation here, A equals P e to the RT, e raised to the RT, where A is our amount after t years. Okay, P again is our principal interest. T is going to be our years again. R is our annual interest rate. And don't forget, R needs to be in decimals, okay? And E is our Euler's number, which we gave you here And again, there's more decimals here, but this is good enough for a lot of our uses. However, your calculators do have a button for E, and it will give you the best usage of E with tons and tons of decimals, okay? So we also have a logarithmic expression or representation of this continuous compound interest, and we get it from this exponential form as well. So all we do is go ahead and divide by p, and we know so this is what we're left over with, and we can take the natural log of both sides. Okay, so the natural log here, I've got basically log base e of e to the rt, so this is going to simplify to just rt. And I'll show you how that happens in the next slide, but we've kind of seen that before. Okay, so this is going to be our logarithmic representation. Natural log of a over p equals rt. Again, my a, p, r, and t are what I have over here. All right, so let's get into some examples here. We're going to convert from exponential to logarithmic form. All right, so here I've got my exponential form with a base of e. Okay, base of e, and then I know that my exponent is the solution for when I'm converting to logarithmic form. And then what is inside my log, okay, that's on the opposite side of the equation, okay? So when I go ahead and set this up, I've got log base e, okay? This goes inside my log, this 9 here, okay? And then my exponent becomes the solution for the logarithmic conversion, all right? Now I said earlier, okay, we don't represent natural log like this. We're going to take this and write it as ln, okay, natural log. So our conversion looks like natural log of 9 equals x, right? So take this same logic, pause the video quickly, and write down what e to the 7th equals x looks like as a logarithmic equation. Okay, so that should look like natural log of x equals 7, okay? Okay, going the opposite way now, going from logarithmic to exponential equations, all right? So again here, this natural log is going to tell me my base, right? Because I know this means I have a base of e, right? And then I've got my solution that's inside the log. And then what's on the opposite side of my equation, that's just my exponent, okay? I'm going to start to set up this exponential equation. So I've got a log base e, okay, again, my exponent is x now, I bring that up as the exponent. And then my solution is what was inside of the natural log. Okay, so that's going to be 18. Okay, so take that same logic and go ahead and rewrite this equation in exponential form. Okay, hopefully this is what you got. We'll go ahead and move on to our next example. And that is going to be simplifying expressions. Okay, so we're going to simplify these expressions the most we can, and we're going to pull on our logarithmic properties, which also apply to these natural logs, okay? So natural log of a minus natural log of b equals natural log of a over b. Okay, so let's use that in conjunction with our power property that says if I have a coefficient out here, I can bring that coefficient out to the front here, right? Or into my exponent, sorry. Bring my coefficient into the exponent, okay, for what's inside my logs. So I'm going to write this as natural log of 8 to the 6th minus natural log of 4 squared. And then we can go ahead and use this property here, this quotient property. And so that's going to be natural log of, 8 to the 6th is 262,144. And 4 squared is going to be 16. All right. So that simplifies to the natural log. We're just simplifying what's inside of the log now. It's going to be 16,384, which we can express as 2 to the 14. Now we're just going to do kind of the reverse of what we did up here, and we're going to take our 14, we're going to bring that out as the coefficient, and our final simplified expression is going to look like 14 natural log of 2. Okay, go ahead and pause. Don't be back at the video. Go ahead and pause and try to simplify this expression here, again using some of our logarithmic properties from previous videos. Okay, hopefully this is what you got. Natural log of 2000y. Go ahead and check your work here, and we'll keep it moving. Okay, next, let's go ahead and solve equations and inequalities, all right? So first thing we're going to do here, I've got 3e to the 4x minus 12 equals 15. let's go ahead and get our e term by itself. Okay, so we're going to add 12 to each side. Okay, and then let's go ahead and divide by 3. And again, I'm just trying to get e by itself. Okay, and you'll see why, because now that when I get it to this point here, when I get my equation to this point, I can take the natural log of both sides, right? And if I take the natural log of both sides, okay, I mentioned earlier that this is going to simplify to whatever this exponent is, right? Because if I have log base 5 of 5 raised to the x, okay, I'm telling you that that equals x, right? That simplifies to x. Why is that? Because log base 5, okay, so if I think of this exponentially, okay, this is saying 5 raised to what power equals what's inside of my log here, equals 5 raised to the x power, right? 5 raised to what power equals 5 raised to the x power? Well, doesn't it make sense that whatever that is going to just be x, okay? So that's why that simplifies to whatever that exponent is when I have the same base of my log as the base of whatever's inside the log, all right? So when I take the natural log of both sides, my left-hand side simplifies to 4x, and then I can go ahead and divide by 4. And when I plug in natural log of 9 divided by 4, that is going to give me my final solution, okay? So go ahead and use that same logic and solve this inequality now. Pause the video, solve the inequality, see what you get. Okay, hopefully you got x is greater than 5.1945. The one step that I want to kind of highlight is going to be our step here where we do what a process called exponentiating, okay? And we've done this in previous videos, but just to kind of reiterate what it's called, exponentiating is when I take an equation, right, or an inequality in this case, and I kind of bring in this base, and I raise what was in the equation, I raise that up into the exponents of this new equation with this new base, okay? So I really exponentiated both sides of this inequality, so then when I had natural log of 2x minus 3 is greater than 2, now I have e raised to the natural log of 2x minus 3 is greater than e raised to the second power, okay? And then with similar thinking as what we did over here on the left, okay, this right here, okay, is just going to simplify to what's inside the log now, okay? So because I have the same base of my log in my exponent, okay, as the same base here, okay, that is going to kind of cancel each other out, and that will simplify to whatever's inside my log here, all right? So this whole left-hand side simplifies to 2x minus 3, and then I can go ahead and add 3 and solve for x from there, okay? All right, last example here, looking at our continuous compound interest. Okay, we're going to deposit $700 into a bank account that gives us 3% annual interest, and we're going to compound continuously. Okay, compound continuously. First of our 3 questions. A, what is the balance after 8 years? Okay, well, after 8 years, okay, our P is going to be what? Our P will be 700. P will be 700, our R will be 3%, but guys, we have to remember that we need to represent R as a decimal, okay? We have to represent R as a decimal. If you plug in 3 when you use R in our equation, which I'll show here, that is not going to be correct, okay? I have to represent R as a decimal, and then T is 8 years, okay? So we can go ahead and just plug in our values here when we're using A is equal to P e to the RT. So 700 e to the 0.03 times 8. Okay, again, R has to be in decimals. That's a mistake that a lot of students make, okay? And then we can just plug this in to our calculators and find our final balance after 8 years. All right, question B, how long will it take for the balance in our account to reach at least $1,200? Okay, so now our A is 1,200, our P is still 700, our rate is still 0.03, and now we're trying to find our time, okay? We're trying to find our years, T, okay? So again, we use the same equation here. Same equation. We're just going to go ahead and plug in everything except for T, okay? Except for T. So in order to solve for T, which is all we need to do here. We're going to divide by $700, okay, and that will kind of isolate our e term. Then from there, we can take the natural log of both sides. Hopefully you realize you can do that because I've got this e term here, and this is going to then simplify to just 0.03t. Okay, so then I can divide by 0.03, and these 0.03s will cancel out. So I just have natural log of 1200 divided by 700, all divided by 0.03, and that's going to give me a time of roughly 18 years. Okay. Now, if you thought back to the concept slides for continuous compound interest, we also had this representation for continuous compound interest, which we could have used, and we eventually basically got to. Okay. However, we could have just used this right from the get-go and divided by r on both sides, and that would have solved for t right away. Okay, so we went kind of the long way around, but you get to the same answer regardless. All right, taking a look at our final question C, how much would have to be deposited in order to reach a balance of $1,500 after 12 years? Okay, so P, our principal, is our unknown. A is our 1,500, and T is 12 years, and we're going to stay with the same rate of 3%. Okay, 3%, again, representing that as 0.03 as a decimal. Okay, using our same equation, okay, we don't know P, so we can go ahead and just divide by e to the RT on both sides, and that's going to isolate P like so, and then we can just plug in everything that we know. Okay, so I've got 1,500 divided by e to the 0.03 times 12, and that's going to give us a deposit of $1,046.51. Okay, so that's it for this video, guys. Good luck with your practice.